Again, welcome to Operating System CS332 class. These lectures, we are going to cover the mutual exclusion and synchronization. So again, in a uniprocessor system, that's a system with only one process. In a uniprocessor system, concurrent process cannot have overlap execution. They can only be interleaved. Furthermore, a process will continue to run until it invokes an operating system services or until it is interrupted. Therefore, to guarantee mutual exclusion, it is sufficient to prevent a process from being interrupted. This capability can be provided in the form of primitive defined by the operating system kernel for disabling and also enabling interrupts. Because the critical session cannot be interrupted, mutual exclusion is guaranteed. So the price of this approach, however, is high, and that's the disadvantage, because the efficiency of execution could be noticeable degraded because the processor is limited to its ability to interleave processes. Another problem is that this approach will not work in a multi-processor architecture. When a computer includes more than one process or one processor, it is possible and also typically for more than one process to be executing at a time. In this case, disable interrupts do not guarantee mutual exclusion. The next is the compare and swap instruction. So this version of instruction checks a memory location against a test value. Now, if the memory location current value is test value, it is replaced with a new value. Otherwise, it is left unchanged. So the old memory value is always returned. So the memory location has been updated if the return value is the same as the test value. This atomic instruction, therefore, has two parts. The first part is the compare is made between a memory value and a test value. Now, if the values are the same, a swap occurs. And this entire compare and swap function is carried out atomically. That is, it is not subject to interruption. Another version of this instruction returns a Boolean value, true if the swap occurred, false otherwise. So some version of this instruction is available on nearly all processor families, and most operating systems use the instruction for support of concurrency. Now in the figure shows here, the A shows a mutual exclusion protocol based on the use of this instruction. Again, that's the compare and swap. A shared memory both is initialized to 0. So we initialize the shared memory both to 0. Now, the only process that may enter its critical section is the one that finds the both equal to 0. All other processes attempt to enter their critical section go into a busy waiting mode. So the term busy waiting or spin waiting refers to the technique in which a process can do nothing until it gets permission to enter its critical section, but continues to execute an instruction or set of instruction that tells the appropriate variable to gain entrance. Now, when a process leaves its critical section, it resets the both to 0. So at this point, one and only one of the waiting processes is granted access to its critical section. Now, the choice of process depends on which process happens to execute the compare and swap instruction next. And another method in figure B, which is again exchange instruction, shows the mutual exclusion protocol, again based on the use of exchange instruction. Here, A shared variable boot is initialized to 0. Each process uses a local variable key that is initialized to 1. The only process that may enter its critical section is the one that finds the boot equal to 0. Then it excludes all other processes from the critical section by setting the boot to 1. When a process leaves its critical section, it resets the boot to 0, then allow another process to gain access to its critical again section. Now, special machine instructions advantage. Now, the use of special machine instruction to enforce mutual exclusion has a number of advantages. One, it is applicable to any number of processes on either a single processor or multiple processors to share main memory. Also, it is simple and therefore easy to verify. It can be used to support multiple critical sections. Each critical section can be defined by its own variable. Also, the special machine instruction disadvantage. These are some serious disadvantages. Example is busy waiting is employed. Busy waiting is employed. Thus, while a process is waiting for access to a critical section, it continues to consume processor time. Starvation also is possible when a process leaves a critical section and more than one process is waiting. The selection of a waiting process is arbitrary. Thus, some process could indefinitely be denied access. And also deadlock is possible. So consider the following scenario on a single processor system. Let's say processor P1 executes a special instruction, example, compare and swap or exchange, and enters a critical section. Now, P1 is then interrupted to give the processor to P2, which has higher priority. Now, if P2 now attempt to use the same resources as P1, it will be denied access because of the mutual exclusion mechanism, because P1 is not yet completed, process is not. Thus, it will go into a busy waiting loop. However, P1 will never be dispatched because of its lower priority, since P2 have a higher priority than P1. So P2 can never be discharged. But at the same time, P2 also want to use resources that P1 have. And this will lead to, again, deadlock problem. So because of this drawback of both the software and hardware solution just outlined, we need to look for further other mechanisms. So again, these are the common concurrency mechanism which we may go through. And we now turn to operating system and programming language mechanisms that are used to provide concurrency. So the table here summarizes the mechanism in common use. We begin in this section with semaphores. So again, our next section, we are going to discuss about semaphores, and the other mechanism will be discussed later in chapter 6 and also chapter 13. So semaphore is an intergent value used for signaling among processes. So only 3 operations may be performed on a semaphore, all of which are atomic, that's initialize, decrement, and increment. The decrement operation may result in the blocking of a process, and the increment operation may result in unblocking of a process, also known as counting semaphore or general semaphore. Again, we are going to discuss this in our next lectures. We also have the binary semaphore, muters. Muters will be discussed in chapter 6, and conditional variable, monitor, event flags, main box or messages and spin locks, which will be discussed somewhere around chapter 13. So with the spin locks, mutual exclusion mechanism in which a process executes in an infinity loop, waiting for a value of a lock variable to indicate a variability. Also with the mailboxes or messages, a means for two processes to exchange information, and that may be used for synchronization. Again, we may go detail on this in chapter 6 somewhere. So that will be the conclusion of these lectures. Again, our main objective in these lectures is to discuss about the mutual exclusion and synchronization. And we discuss about two ways of doing this, either interrupt December, and also in a few lectures to come, again, we may go more detail, I think somewhere around chapter 6, as we said, and also chapter, again, 13. So the main method, compare swap instruction, we went through, and also exchange instruction. But again, these methods are the most simple way of, again, implementing the concept of mutual exclusion synchronization. But they have a very bad disadvantages, especially by the starvation and deadlock. And we may go details on that. So again, wish everybody the best, and thank you.